If you have a problem and you want to use an algorithm to solve that problem, there's generally going to be more than one algorithm that you could use to get to the same answer. An algorithm design strategy is a methodical approach that is used to create efficient algorithms. Choosing the right algorithm design strategy depends on the specific requirements of the problem. There are 5 main design strategies that you're going to learn in this video, and we're actually going to start with the one that's most inefficient, that being the brute force approach. This is essentially as it says in the name. You brute force your way to the solution. This is often the easiest way to come up with a solution, but if there's another design strategy you can use, then you shouldn't resort to using brute force. Brute force differs from the other design strategies. Where those can generally only be applied to certain types of problems, you can technically use brute force to solve any problem algorithmically, although you shouldn't really do that. That being said, there are some cases where you may want to use brute force, and those would be if the problem you are solving is really small, or for benchmarking, which is where you compare the performance of one algorithm against a standard, that standard being the brute force algorithm. Moving on to divide and conquer, which is also pretty versatile. It can be used for sorting and searching problems, but it's not limited to that. It involves breaking down a problem into smaller problems, which can be broken down into smaller problems and so on. And this is typically done recursively, so we stop when we reach the base case. At this point, we solve and combine the subproblems until we've worked our way back up and have solved the main problem that we set out to solve. Next up, we have the greedy strategy, which solves problems step by step and makes locally optimal or greedy decisions at each step, in the hopes that this will lead to a globally optimal solution. The algorithm only cares about the decision being made at the current step. It doesn't care about the second order consequences of that decision, and once it's made a decision, it doesn't change its mind, making the strategy very efficient. The solution found will usually be good, however, there is a chance that it may not be the best one. Backtracking algorithms explore multiple paths on the way to finding the solution, or solutions, to a problem. They utilise depth-first search, so explore a single path until either a solution is found or a dead end is hit, before backtracking to the previous decision point and taking another path. These algorithms are represented visually in a state space tree, which shows all the possible states that can be reached in the process of solving such a problem. The root of the tree is the initial state, and each leaf represents a solution or a dead end. Dynamic programming can only be used for problems that have overlapping subproblems. We solve each subproblem only once and store the solution in an array, so that when we come across it again, we don't need to recompute it and can instead just return the value that's already available to us. There are 2 types of dynamic programming: the top-down approach, which is an optimization of recursion, and the bottom-up approach, which builds solutions iteratively from smaller subproblems up to the main problem. If you want to explore any of these algorithm design strategies further, I've made individual videos about all of them, where we'll have a more in-depth look at them, see how they work and where they're used, and also see them in action with some examples. Hit that subscribe button down below and then check out the video on screen to learn more about computer science. I'll see you there.